My name is David Aghassi. I work on the front-end platform team at Robinhood, and I'm going to be talking about how we built our recent application, Robinhood Legends, and optimized for scale as we built out. So really quick, Legends, for those of you who may not know, is an advanced trader application that you can use directly in your browser, no downloads required. The things I'll be covering today are the size of the team and the code base, the design constraints that we placed on ourselves as we built out this application, patterns that we used to scale on a larger front-end code base, hurdles that we faced when scaling those patterns, and finally the outcomes. So as of last month, the code base is about 1 million lines of code, 8,000 files, 1,700 build files, spread across 30 web engineers. This doesn't include any third-party modules or the rest of our monorepo code. In terms of design constraints, we wanted everything to be within Bazel, including local development, which was definitely a challenge. We wanted to be ECMAScript first for JavaScript so that we were adopting the latest web standards. We wanted to make sure that we were meeting the expectations of web engineers and being ergonomic to the patterns that they wanted in terms of running scripts. And additionally, we wanted build files to be generated on behalf of the user so that there was no need for them to be writing build files by hand. So in terms of patterns, we came up with a dual macro pattern to scale. On the left, we have a source file pattern, which for any file that was used within the production code base, it would run through this source macro that handles image compression, type checking, transpilation, linting, some coverage logic, and CSS transformations. On the right, we have a test macro, which depends on the first one, and then additionally runs jest. This is going to be hard to see, so please look at the slides, but these are what the generic macros will look like, so you can look at them afterwards. Additionally, for Gazelle, the way we were able to accomplish this was using Aspect's JS Gazelle plugin with a couple of patches. So you can use that plugin with map kind on TS project, and in our case, we mapped it to the source macro, allowing Gazelle to generate build files on behalf of the user for source. And then you can, if you patch it, I think it might be supported now, add a test target, and for that, we passed it our test macro. That way, Gazelle manages both source files and test files. One little note here that I figured out, if you make a folder within your source directory and you do a map kind again within that folder, you can support multiple test types. So we also have playwright tests within our code base, but they live in their own subfolder. Lastly, in terms of compilation, we have a top-level RS-pack target, which all of our dependencies ladder up to, given a single entry point. This is an example of that target. Again, please look at the slides afterwards so you can see a more readable version. So some of the hurdles that we faced. Not all tools understand Bazel. We found this specifically with Playwright, needed a couple of internal patches to make it support running locally. We initially had some slower development cycles than we would have liked until we were able to optimize the build graph and make running iBazel locally a lot faster. At first, Gazelle plugins didn't support tests, so as I mentioned, we patched that. Coverage was completely custom to gather coverage from across 2 different test runners with correct line syntax highlighting and going through the Bazel coverage reporter. We had a lot of issues with the broader JS ecosystem, not within Bazel, just having ESM forward modules. There was additionally issues with getting Playwright visual snapshot tests between macOS and Linux. Little heads up there, if you can build a container on macOS for Linux, you can schedule your Playwright tests in that container and take the output of that as your snapshot to have CI parity. And then lastly, build file generation was not smooth at first. We used a Webpack plugin to kind of prompt people to do what they needed to do until such time that we were able to start utilizing iBazel fix commands. So tips and strategies, we went with put a build file in every folder. This may be different depending on your code base, but for us, it was very helpful. We opted for Rust-based tooling as much as possible because of the speed benefits it provides. As to the prior talk, we also use isolated declarations and saw a huge improvement from doing that. On larger, heavier tests like Playwright, we needed a default sharding amount of between 12 and 15 just to avoid flakiness or noisy neighbor problems. And then specifically for Playwright, because we're using web bundles, we have to produce a production bundle, or the actual test time to start was about 30 seconds. So impacts and outcomes. On CI, we benchmarked this application versus our older web application that was on rules nodejs, and it's about 55% faster, P95 and P50. Over the course of the production of the application, we were able to get build file generation down from 2 minutes to about 20 seconds. Now we have developers who can onboard with a single command, and they can make PRs same day without environment setup. We were able to get our flakes down to a manageable amount, about maybe 10 a week, and our cache hit rates are way higher than they were before. Also, developer satisfaction in the web community with Bazel has improved dramatically since this, as we have abstracted most of the Bazel problems from our developers. And that's it. I'd like to thank you all for coming.